Okay, hi guys. So in this lecture, we'll be seeing more on the parallel reactions. So we have already seen that uh, reactant A converts into B and C at two different constant constants, which is K1 and K2, and the overall rate constant is K. So we wrote that K would be equals to K1 plus K2, or we can also write that 0.693 upon half-life of half-life overall would be equals to 0.693 divided by T half of first reaction plus 0.693 divided by T half of second reaction. Okay, now let us see that what is the net rate of disappearance of A. Rate of disappearance of so it would be minus dA by dt would be equals to K1 times A plus K2 times A, or we can write that minus dA by dt would be equals to K1 plus K2 times A. Okay, and from here we can write that minus dA by dt would be equals to K times A. Okay, so K is the overall rate constant for the two reactions, means two parallel reactions. So from here we can write that concentration of A after time t would be A would be equals to A naught e to the power minus kt, where K is nothing but K1 plus K2. Okay, and we can then write that K1 plus K2 would be equals to 1 upon T ln A naught divided by concentration of A at time t. Okay, so before going forward, please remember this: A naught would be equals to, or rather A naught would be equals to the concentration of A at any point of time t plus concentration of C plus concentration of B plus concentration of C at time t. Why is this the case? Because in the parallel equation or in the parallel reactions, only the A is getting dissociated into 1 mole of B and 1 mole of C. Okay, so whatever B and C is formed at any point of time t, the same amount would have been deducted from the initial amount of A. So A naught at any point of time would be equals to sum of all the number of moles which are present in the reaction mixture. So that would be 1 minus x minus y plus x plus y. X and y can vary according to time, but the sum will not vary and the initial concentration will always remain the same. Hence, this verifies our the fact that A naught would be indeed equals to AT plus BT plus CT. Okay, so this is very important in this case. Okay, so now we can write from the above equation that K1 plus K2 times T would be equals to ln A naught is nothing but AT plus BT plus CT divided by concentration of A at time t. Okay, so we can also write that concentration of B divided by concentration of C would be K1 upon K2, because this is a respective rate constant when B and C gets dissociated from, rather get formed because of dissociation of A. So this was K1 and this was K2. So B concentration of B by concentration of C would be ratio of rate constants of the respective reactions. So from here we can also write that dp by dt would be equals to k1 times a, and dc by dt would be equals to k2 times a. So if we divide the two, we would again get that dp by dt divided by dc by dt would again be k1 upon k2. Okay, so moving forward, we know that dp by dt is equals to k1 times concentration of a, and this can be written as dp by dt equals to k1 times concentration of, or this is concentration of a. So what can concentration of a be written as? Concentration of a can be written as a naught e to the power minus k 1 plus k2 t. Okay, so just rearranging the equations here. So we can write dp by, rather db would be equals to k1 times a naught e to the power minus k1 plus k2 t dt. Integrate the equations on both the sides. So we would be getting that b would be equals to k1 times a naught times e to the power minus k1 plus k2 t divided by minus of k1 plus k2 plus c. So from here we can write that when t equals to 0, then bt is equals to 0. Okay, so this is bt. So just putting this value in this equation to get the value of c. So we will be getting 0 is equals to k1 times a naught divided by minus k1 plus k2. This would be plus c. So value of c would be k1 a naught divided by k1 plus k2. If we put this again in this equation, or in equation number 1, we can get that bt would be equals to k1 times a naught e to the power minus k1 plus k2t divided by minus k1 plus k2 plus c would be equals to k1 times a naught divided by k1 plus k2. So just solving it, we will be getting that bt would be k1 plus k2 k1 a naught times 1 minus e to the power minus k1 plus k2 t. Okay, so please remember that this is a very important formula. Oops. Okay, and similarly we can get that what will be the percentage of product distribution. So percentage of product distribution would be k1 divided by k1 plus k2 into 100. This is for B, and for C similarly we can write it would be k2 divided by k1 plus k2 into 100. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing one more example wherein A dissociates into 2 moles of B, and the same A parallel dissociates into 3 moles of C. So how would that compare with this whole derivation? We will look into that, and then we will be seeing series or consecutive reactions. So till then, good luck and goodbye.